Okay, I guess, should I just get started? Jump in?
Yeah, so
Awesome.
they're joining now, so we can start.
Okay.
Yeah.
Yeah. Very cool, very cool. Yeah, I know folks might be streaming in right now. Welcome to another installment of oh, let me share a screen. Get all set up there. Make sure I got my so I'm sharing the screen. Wait, is that the whole screen? Let's get the annotation going. There we go. We've got our annotations. So you guys can all see the screen and so forth.
Yeah.
Awesome. Good. We have Janica here. Awesome. Um, so today we will be picking up where we left off last time. And we're going to be spending some time getting to know the next couple weeks, the fun, interesting, engaged part of the course where we're going to build cutting edge technologies, cutting edge product, cutting edge AI. So let's just jump into some logistics, and then we'll talk about part two. We're going to pick up exactly where we left off last time. All right. So you've seen a slide like this before. Let me just get the chat window for you guys up and running. So remember, feel free to send me anything in the chat, right? Use the chat to respond, answer questions or ask questions. I'm always getting like all the different screens set up. Okay, so as we mentioned last time, there's a couple logistics around the class. Right now, we're going to get into the build phase where folks can roll their sleeves up, get their hands dirty. I know that there's been a lot of good kind of like lectures that you guys have been engaging on, learning what's under the hood of this AI stuff, but really gaining an experience of building and solving problems at the highest level with AI is one of the missions of this course. And so we're going to get on that journey. So remember, everyone's invited on to Piazza. You should have an email in your inbox. If you don't, you should have had it last week. I'm not sure if that all worked out, but like if emails went out, but I did send reminders today. So if you don't have an email, get on the Discord or communicate with Loggy to make sure that you guys are plugged in. Loggy, let me know real quick. Were you able to get onto Piazza?
Not. I got the invite, Jason, but I didn't log in. But
Okay.
yeah, we are
Okay.
communicating. I have created an email group, so all the things
Good.
are shared with them through that. So
Awesome.
I will invite them also by maybe latest by tomorrow. Yeah.
Sure. And indeed, so Locky is really the kind of key point of contact for the whole class when it comes to getting organized. Online courses, digital courses or remote courses are it's always important to be able to have a single point to connect with to make sure that you're plugged into all of the activities and fun stuff going on. So do reach out to Loggy if you're like, wait, what email? Wait, how do I get on the Discord? These are the communication channels that are tools that are made available to you guys to be able to kind of stay connected and, coordinate when it comes to the formation of your groups, 2 to 5 people. We're going to need to have the first groups kind of formed by next week. What'll happen next week is we're going to look at a couple research papers, right? And that process is going to allow groups an opportunity to present to the course those papers, right? And this is part of the criteria that is evaluated when it comes to the prizes for the project competition. And so come next week, we're really going to be calling upon groups to engage in the class, enhance their general growth learning, and be competitive for the stardom, right? AI stardom through the means, through the form that is this course. So the project readiness stuff is going to start today. We're going to have a special presentation from some folks I'm going to introduce shortly on the next slide. And these project readiness assignments, there's going to be 3 to 4 of them. They're essentially guardrails for you guys to build something from 0 to 1, right? Using awesome cutting edge tools, generative AI models to build AI experiences from soup to nuts, from 0 to 1. And you're going to have a guided tour through that, such that when you start to build your own thing, you would have had the practice and the know-how as to how to wield these tools to build interesting AI applications and products. So this is going to start warming up today, and there's going to be 3 or 4 of these over the next 3 or 4 weeks. Okay, so this is happening. So awesome. Let's actually get in and do cool stuff. And then we'll have the competition, and more details will come about how this is going to be structured across participating groups. Anyone that's interested, if you have groups already, or if you want to find groups, or if you're eager to participate in the project competition, indeed connect with Logi. And make sure that he is aware. What I'm going to ask him to do is to create a spreadsheet of all the groups that are participating, so I could make sure that I create time and opportunities to do one-on-one sessions with you guys, just to see how you're doing, give any advice, give any feedback as you go on the journey, right? So I'm going to make myself available to these groups that are participating. If you have a group, or if you want to find a group to participate, definitely let Logi know, engage on these platforms to make sure that you are, we're aware of your interest and enthusiasm to be involved. In addition to the cash prizes, of course, there's also a certificate that comes at the end of the course for participating groups. So I strongly encourage anyone with interest to engage and participate. At the end of that journey, you will be capable of building real AI experiences. So any questions on that, feel free to drop it in the chat. As I go to the next slide, right? So don't hesitate to just ask me anything as it relates to the last slide. Now, so there's 2 members of the incubation lab / Giseki Labs that are going to be there for the entirety of the journey through the projects and through the assignments. So there's Savini, who, like, folks at University of Moratuwa may recognize Savini, and Jayanika for that matter, because both of these guys have lectured or taught courses at University of Moratuwa. So these might be familiar faces, but if they're not, these are very, very talented, awesome people who are, both frequent campus there, and also participate and are very involved in the incubation lab. Indeed, these guys are participating in inventing some of the technologies, of course, all open source, all for the world, but they're participants in the invention journey of relevant technologies that you guys are going to be using. Indeed, Janica, and we should do this next time, Janica built this really crazy video game using the tools that you guys are going to learn to use, and generative AI, GPT-4. He built a video game where the levels of the game is generated by a GPT. So it's like AI is creating the game content as you play the game in real time. There's a GPT watching and constructing the next level as you play it. So maybe we'll have Janica demo that next time, so you guys can see what's possible with Gen AI these days. What kind of new new things are even feasible now. And so by the end of the journey, we want to raise you to that level. These guys are going to be available to communicate, connect, and engage with you guys and guide you guys. And they're also going to be presenting after I'm done. So I should probably go for 25 minutes to wrap up the last lecture. And then these guys are going to hop on and present a couple slides introducing you to the tools and the stack that we're going to use in this seminar. Okay, so that's coming at the end. Get to know these folks. this guy is going to be a PhD student at University of Michigan soon. And who knows, maybe this person too. We'll see. Anyway, just get to know these folks. These guys are going to be around for a while, and they're going to be doing some crazy AI brilliant stuff for the world. And so this is a great opportunity to network as well for everyone in the class. So I encourage you to do that. Yeah. Any questions on that before we hop right into where we left off? Cool. All right. So part 2. So what we're going to do is, if you remember last time, I'm going to take you on like a 20-second page it back into your mind, what we talked about last time. And then we're going to jump into from that point forward, right? Remember, we're going on a journey of understanding exactly where ChatGPT came from and where generative AI came from as we know it, the world disrupting generative AI that we're all using and enjoying. And so we looked at this last time. We reasoned about how words turn into numbers. And then we looked at a feed-forward neural network that takes in numbers as words and puts out a word that's also in the same numerical representation, right? One-hot encodings. And this was indeed used to create the next stage of the journey where we had a happy accident and we came up with something better to represent words where there is an understanding of the meaning and semantics of words in that representation, right? So if you remember, we used, after training this type of thing, which is called a continuous bag of words feed-forward neural network that will take in an input set of words, which is a window of words from text, and predict the missing word out of that window, right? So if you're looking at, this would be a window of 3 words. You take one word to the left, one word to the right, and then you predict the word that's missing, okay? So cat sat on is probably most statistically likely to be the word that might be missing in between these 2 words. And then once you train this model to do a good job, you can take advantage of this, the weights of this model, the activations in the hidden layer, to come up with a better representation where you can have this word vector, right? And this word vector can be n-dimensional because you're using the richness of the fact that you can have floating point values, let's say, to be each of the dimensions of the vector. Okay. So we talked about that last time. It's on video. You can check it out, okay? To catch up on that. So do that. But we did this, and then we observed that when you train a model in that way, predict the missing word, that representation space has deep understandings of the world, right? And that was an accident. As even admitted to in this paper, we were trying to find a better way to encode words than one-hot encodings, and we actually discovered we can learn that king minus man plus woman equals queen, right? But there was a problem with that, if anyone remembers, like the problem we talked about. So the problem was, yeah, okay, that's great, but can we do better? This is the ethos of engineering science. This is what we all do. You have a PhD, you are aspiring to be an academician, you're aspiring to a PhD, you want to be a computer scientist, underscore on scientist. This is the driving question of everything. Can we do better, right? So of course the scientists are like, can we do better? Well, here's an insight of a drawback. An insight of a drawback of using a model like this, which is a feed-forward neural network, is that the input layer, there's no way to capture the sequence-to-sequence relationship between the words in that older neural network. You can't capture it because the input layer, once the hidden layer sees the weights that come from the input layer, it doesn't know which order the words were in. So the man blank the dog is the same representation as the dog blanks the man in the hidden layer, right? So what is that, pets? Is that bites? Well, there's information you lose that could be useful to make the model smarter. So maybe we can do better if we were to represent the sequence-to-sequence relationship between words. Okay, cool. Next world-changing event. A relatively old technique called recurrent neural networks is exactly built for that. Time series information, where the order of the information matters. Words have that property. Frames of a video, right? You don't want to randomize which frame shows up when in a video, or you lose all the knowledge that's in there. Same thing with words. You don't want to randomize the word order in every sentence of a book, because then you couldn't read it. And so, there might be a neural network that can capture more goodness. Recurrent neural network. And the key property of a recurrent neural network was, every word will see what came before it. Or let's say the hidden weights of what came before it, or the hidden representation, let's say, of what came before it in a chain order where the sequence of information, the neural network activations here, there's an imprint of the activations on word one. On the next word, the imprint of that activations goes in as part of the input to reason about. And then that imprint also manifests in the next imprint of activations. And when I say activations, just think of neurons firing, right? So, when we talk about representations, we're really talking about, and the way that I put it intuitively is, if I say the word apple, that's the input into your brain, and then your neurons will fire in a certain pattern. If I was to take a photograph of your neurons firing when you think of the word apple, that photograph is a representation of your intelligence for apple, right? So an embedding is that photo, right? It's a photo of your neurons firing. This is a simplification, but it's actually analogous to what we mean by representation or embedding, embedded representation, etc. It's like a photo of your neurons firing in your head. It's an imprint of what is in your brain when you have apple. So that's what these H's are. These are imprints. So we're actually looking at the previous imprints while we look at the word, and that's how we get that sequence to sequence, that ability to capture the context of the word in terms of what order the words come in. So we wanted to use one of these, and we happen to use a version of this called LSTM. I'm not going to get back into it, but this is how we made the improvement. And we did better. This paper beats the Word2Vec paper. This is the Elmo paper, right? You can check these papers out to see. And this was also a game changer in the academic community. Of course, AI, this style of AI wasn't hot on the, like Siri wasn't using this. Even though Siri was invented like, I don't know, 3 years before this paper, Siri wasn't using this hot tech. There's always a trailing in the market from what the scientists know about. There still is one now. The challenge to you is to identify that gap. Like, the market is all gaga over GPTs, but what are they missing? That exists. Anyway, we talked about that a little last time. Check the last video for insights there. But yeah, so can we do better, right? Comes next. This is the ethos of the scientist. So can we do better? Okay, cool. So we got sequence to sequence. The model's smarter, but there's an issue, right? Now we have a dependency, as we talked about last time. That dependency is a painful dependency because you can't train in parallel. You have to get your representation of each word before the representation of the next word. Remember that photograph of the neurons. And so you create a dependency where you can't do it all in parallel, right? Of course, Google doesn't like this. Google is about data centers and servers and parallelism and scale and GPUs and right? So they're like, this has a fundamental limitation on scale, even though it captures representation. So that led to the inventions of the transformer, right? Which we talked about last time. And really, the key part of the transformer is the attention mechanism, right? Where the representation of each word simultaneously factors in all of the words in a window, right? And the cool thing is each word can do that processing simultaneously. So each one of the words in a sequence can have this attention softmax, which means it's a probability distribution as to how much I pay attention to each of the words, and then you can train that whole thing in parallel, okay? I showed many ways of looking at this, but this is the most compelling example. If you look at these two contexts, right? These are two contexts that are different by just one word. But the attention mechanism, the representation, the neuron firings when of the word it in this sequence should be affected most by the fact that this is animal, given this context, this sequence, the fact that this is street, given this context, this sequence. It corresponds to animal in this context on the left, right? So you have an attention mechanism that says in this context, and this context is how we capture that. We're approximating the sequence-to-sequence relationship information capture capability of an LSTM. We're capturing that by looking at words in context and how that word should pay attention to or be affected by the representation means the photograph when your neurons fire of other words in the same context, right? So it is animal here. So the neuron firing, the way your neurons fire here should be closer, the representation here should be closer to the way your neurons fire there, which is the representation there, right? Of animal in this particular context. But if you go to another context, let's say this context, where there's one word different, it's not tired. The animal didn't cross the street because it was too tired. The animal didn't cross the street because it was too wide. It, in this context, should pay more attention to street, right? So, because it corresponds to street in this context. So, the two words from now will affect the way that this neuron firing happens, because this neuron firing is going to be more corresponding to the word street. That's the inside of attention mechanisms, right? Just covering it again, so that I can hit. That's the secret. Now, the benefit of this, guys, the benefit of this is we don't have to go word by word and pay. And I was going to say pay attention. Don't want to confuse you, but we don't have to go word by word. We can look at a whole chunk of words and then simultaneously learn what the distribution of attention should be on the whole context of words. So this can all go through a machine and be trained simultaneously because you're looking at chunks of words. That's the attention mechanism. Game changer. Feel free to hit me with any questions in the chat. Remember, I can't see faces, so I can't see if it's confusion or it's like, nah, I got it, you know? So yeah, hit me in this chat. I was about to say Discord. So yeah, anyway, that's it. That's attention. And then we built this whole thing. I'll just go 2 slides. Then we built this whole thing out of that, which is a lot of typical neural networks. This is feed forward. This is the word to vec thing. We like feed forwards because it's super embarrassingly parallel. But then we have these attention heads, multi-head attention. We have these attention components in this neural network architecture. Multi-head just means you're creating multiple attentions at the same time. It's kind of like multi-dimensional attention. So of course you have one way to pay attention, one distribution over words that matter, but you can have multiple such distributions over word metal. So they call it multi-head attention, whatever. Long and short of it is this is just that attention mechanism. And the attention mechanism is a probability distribution. That means that all of the values here are coefficients that sum to 1, right? So this might be 0.9, this is 0.01, 0.01, blah. It sums to the value 1. It's a probability distribution. And all it does is it modulates, the coefficients is applied to the representation of the value, they call it, but the representation of each word, right? So this is just a set of values as wide as your window. So let's say your window is 10. Let's say this is 10 words. You'll have 10 values between 0 and 1 that sum to 1. that are gates as to how much, coefficients as to how much that value of the other word should be summed into the value for this word, right? So that's actually what the attention mechanism is in a nutshell. As I said in the prior course, I encourage folks that are curious to dig deeper. I'll talk a little bit more about it on the next slide, but like there's a whole course. I mean, there's a whole course for how this works. I'm giving you the complete description at a high enough level that you can understand it, but at a low enough level that you're an expert, essentially, right? That's the thing to remember. Okay. So Google had this attention all you need. Oh, Google created this transformer. And this is kind of where we left off last time. And this is the same mechanism, right? And I'll just, I emphasize this just to show the beauty of the construction and just to intimate or just to give an impression, let's say, of the artistry between formal scientific math and engineering that comes to what I was calling neural network alchemy, right? The formulation of these neural network architectures. This one's particularly cute. It's particularly cute because it's designed as a query key value store in a neural network. And these things are weird to think about because these are just weights. Okay, I'll explain just really quickly what's happening here, right? This looks like super complicated, but it's actually quite simple, right? As we said, embeddings is essentially a set of activations, which is a picture of neural networks when it sees the world with the word. Let's say these are, if you just looked at the word by itself, it's the way your neurons fire. And then it's like, oh, dudes. And so like, this is, by the way, this is golden, right? Because I don't think anyone explains it. I've never heard anyone explain it like this. And I think this will allow anyone to understand what's really happening. So it's a picture of the way your neurons fire. When you look at the word by itself, this is essentially the input, right? This is actually usually like a glove or word-to-word embedding, whatever, it doesn't matter. But so if you looked at the word alone, that's how your neurons fire. And then everything here are learnable weights, right? Which means that this is input, this is output, okay? As we looked at the other neural networks, your input is, this could be a one-hot encoding if you wanted. Of course, that's a terrible idea, as we talked about before, but this is like word alone. And then this is the output, the representation, the summation of the neurons firing, the picture for your transformer. And then the interesting bit is, right, this piece here is all word independent, right? This is all like word independent. And then you notice this box comes out and now we're looking at the window of words, right? So we have a query, a key, and a value for every word. And as you do this inference, right? So this is the feed forward inference. As you go from input to output, at this point, you start to look at the keys of all the other words in the window, right? So you have this hyperparallel, right? And then you look at all the keys in the window and you turn those into scores, which is your query, which is related just to this word. And then the keys of the other words, and you use those to get a score across your window. Now, you know, this is usually 1,000. Imagine you have a neural network where you can only look at 2 words at the same time. Of course, this is like 4,000 in ChatGPT. So you have these numbers. You can reduce them, and this value is a heuristic, right? Like the paper describes it as, oh, we tried a bunch of values, this one worked best, right? To kind of reduce the numbers. And then you take these arbitrary values and then you turn them into a probability distribution. You turn them into coefficients such that the coefficients sum to 1. That's a softmax, right? So you sum all of these, and then you take each value divided by the sum, et cetera, et cetera. Let's just say, right? Of course, there's some sigmoids in there, but so you turn it into a probability distribution. So whatever these values are, and then this probability distribution, that's your attention. That's how much you let the values of the other words impact your sum, right? So your softmax times the value will give you the sum, which is the output activation. So this is contextual. So this value is going to change based upon what other words are in the window from this point downward, right? So that's the basic functioning of an attention inference. And it's a beautiful thing. And I encourage folks to, you can go to YouTube if you want to see better, more detailed descriptions of this. You could read the papers. But this was the invention that has rocked our time, you know? Okay, good. So we have that. We have the transformer, right? Now we're out of the recurrent neural network era. So we're not, what is it? We're not doing sequence to sequence with the dependence on not having the scalability about where you can look at multiple words at the same time. And that's in the form of this transformer. There's a lot more details, like the difference between encoder, decoder, etc., which I'll talk about briefly on the next slide. But it's a very interesting invention, this thing. And it's at this point, we got BERT, and BERT wasn't even world-changing yet, right? So the transformer was invented, and this is what Google was harping about. Immediately after ChatGPT came out, they had a press conference where some of the scientific leaders at Google in the press conference said, today, it was such a knee-jerk reaction, right? Because they wanted to unveil their answer to ChatGPT. And in the beginning of that talk, I encourage people to find this online. In the beginning of Chat Talk, they're like, guys, all around the world, I want you to know that we invented it. What you're enjoying right now was us. We did the transformer. Please, guys, just know that. Stop. Give us some love too, Anyway, so this was going on. This is all Google stuff. And of course, the scientific community, the AI community was like, oh my God, this is amazing. This is mind-blowing. King minus man plus woman equals queen. Oh my gosh. And like nobody cared, right? Because we didn't have that moment where a 5-year-old could use it and be like, oh my God, this is amazing. Anyway, so we had BERT. Of course, GPT was another. So BERT is one way of using the transformer where you just use the pictures. Remember the representations, the neurons firing. So that's the BERT style of AI with the transformer. Just give me the representations. It's very similar to the word to vec style, where you have this vector space and you can do cosine similarity and different mathematics in that vector space to get things like king minus man plus woman equals queen. Then there was the GPT style, where you just use the decoder. And a way to think about this is once you train this whole thing, you could just use this piece, right? Because at this point, basically at this point is where you get the embeddings. And that's the neurons, the apple as represented of the picture of your neurons. You get it from the encoder because the word apple goes in here, and then you'll get a representation for apple, the neurons firing here. Now, this part of the neural network is the decoder part. And this is the part that writes text. So it'll take in some kind of representation, or it can take in a sequence of words as a GPT trains it. It takes in something, and then it just writes a sentence for you, okay? This is the decoder part. This is the GPT style, right? So the GPT style just is autoregressive. It looks at the previous window of words to predict what the next word should be, then the previous window to predict what the next word should be, et cetera, right? Just ignore this for now. Don't worry about this, right? Just don't worry about that. But this is the GPT era, right? Because this is that recurrent neural network thing that nobody uses today, so it doesn't matter. Anyway, so after that happened, So we had BERT. BERT was huge. The neurons firing representations are rich. Then we had this thing. It's called T5. Transformer 5? I don't know. This was Google too. This is Google too. So Google was crushing it, dudes. Like Google was super crushing this space. Like it really is a travesty of, I mean, honestly speaking, Google was doing the Einstein work of discovering E equals MC squared, and OpenAI was doing the let's build a nuclear reactor work, right? So maybe they were like more like Oppenheimer. No, that's the bomb dude. No, like let's build a nuclear reactor out of this tech. They're like, okay, we got the science. We know how much energy can come from it. We know how we got to split it theoretically. Let's just build a machine that does it. That's OpenAI, right? And you know, they're alchemists on a different level, right? So you have your alchemists in the neural network, then you have your alchemists into the machinery around the neural network. There's many ways you can have massive impact. So anyway, this is like a Google paper. It's exploring the limits of transfer learning with unified text-to-text transformer. This term, transfer learning, was brought to us by Google, popularized by Google. We can't say that they're the first to I coined the term, but this became the term everybody used because of the BERT paper. That paper I just I showed you, the BERT paper, right? So, gosh, I can go on about this stuff forever, but I gotta be conscious of time. Anyway, so they're like, oh, exploring the limits of the stuff we're doing with this unified text transformer, and this actually came from the GPT thesis. This GPT thesis. So this is BERT is a let's just use the picture of the neurons firing way of thinking about AI. This is, let's just take the decoder after you've learned a bunch and just have it write sentences for us. And like, that's one way to think about AI. That paper that I just showed you, Exploring the Limits with Unified Blah, did two things. It said, well, why don't we just combine both of these, an encoder view of the world and a decoder view of the world, and see if we can get more intelligent? Guess what? T5 was more intelligent. We're not using T5. And this is, let me just explain this to you. The truth and the right answer doesn't necessarily imply what'll be the dominating popular thing. There's a lot of processors that, I could go on a tangent. I was gonna say, you know, Apple's iPhone is the best phone, but there's a bunch of phones that are faster, right? Or whatever, Android phones. So it's not about having the best, it's about, you know, what you offer the market and how you talk to the market. So anyway, that long story short is indeed the T5 paper showed there's something better than GPT. The T5 is a very fascinating paper. So that's one thing it did, but that's a footnote now because nobody cares. They're just like, give me the GPT. The other thing it did is it said you can solve many different problems just using words, right? They didn't call it zero shot yet. But they actually introduced zero-shot learning. I don't think this paper uses the word zero shot at all, but they actually introduced the concept. This is many different tasks in one model where you formulate the task being solved with words. It's actually might be a footnote, but it's like nobody talks about it. And it's actually a really important piece of history that folks shouldn't forget. And it really, look, it's why Google is right. Google did invent a lot of this shit, but they just never brought it to market in a way that made them very popular for it. It's kind of, they're not wrong. And I'll tell you the reason. I'll just say it real quick and we'll move on. The reason they didn't bring it to market is because big companies are afraid of risk. The thing that was business practice before ChatGPT, business practice was if you're a big company, you don't release a model where you don't know what it'll say. Because of liability, you'll get sued up the wazoo. It's going to be racist. It's going to be sexist. It's going to be hateful. It's going to be wrong. It's going to fake data. Liability. Before ChatGPT, the consciousness of all of the commercial market believed the same thing. You never release a model when you don't know what it says. It's too high risk. And so, of course, Google wasn't like releasing products with this stuff because you don't know what it'll say. Of course, the startup, OpenAI, which is technically a startup, was like, yeah, we just care about knowledge for the world. We are just trying to invent, what was it, AGI, which is this stuff, right? This is prompting is AGI, inventing AGI. And so we're just going to release stuff because we're a startup. We don't really care, right? And so they just released it, right? Like, oh, sue us. I don't know. Investors are going to pay the bill, whatever. So they did that and they just changed market appetite and attitude. And now Google's like, oh, crap. Like, we're going to die because of this. Anyway, all right. Long and short of it is T5 was legit. And we got to give them credit. But then after T5, OpenAI was like, well, you know what? We do really like this prompting thing. So like, let's just take the same GPT-2, like literally the same GPT-2, which was like small, like BERT, and let's just make it bigger and see what happens and train it with the internet, right? Let's just make it bigger and just train it for $5 million. We just got to check for $5 million from investors. Let's just train this model and see what it is. Indeed, they called this space flight research because they're like, we're going to build a rocket and we're going to target the moon. And I think we might get there. Let's spend $20 million on it. It's like the same kind of thought process for GPT-3. So that they did that. This was GPT-2. It was kind of BERT scale. And they're like, let's make it bigger. And so, and this is like approximately to scale. So they were like, let's take it from this size and make it that big. But wait, I ran out of room on this slide. We need another page to show how much bigger it was. Let's add this page. It's like, no, wait. We still ran out of room. Let's do another page. Okay, good. Now, we still ran out of room. We still need one more page. Like, that's how much bigger they made it, right? Much, much bigger. $5 million to train it one time at the time with the GPUs we had. Of course, things are cheaper now. This was 2017. I can't remember. 2018 maybe, 2017 maybe, or maybe before that. Something circa 2017. So they did that, and it was like, we would actually need a few hundred more pages to do it properly to scale. So then they took that massive model and they trained it on the internet. And then it just got smarter. And then they really popularized this term in a paper. They wrote a paper about how much smarter it got. Language models are few-shot learners. Look at that, few-shot in the title. Zero-shot, few-shot. What was it called? Zero-shot, one-shot, few-shot. Those popularized that term, and that term was all the rage for like 3 years. Then the community has now stopped using zero-shot learning or few-shot learning or one-shot learning, and they've replaced that term with a new term. It's called prompt learning or prompt training, which is a terrible term. I hate that term because you're not updating the weights of the model. You're not really training it. But they're prompt learning or prompt training or prompt engineering, right? So everybody's heard about prompt engineering, but of course, the scientists don't want to call it prompt engineering in their papers. They need something more scientific sounding. So now people are like, prompt training. So it's whatever. But this, I like this term better. And it was all the rage. But this is a GPT-3 era. It's an era that lasted like 2 years. Microsoft gave OpenAI $1 billion at this stage before ChatGPT. When ChatGPT came out, Microsoft was like, okay, let's give you $10 billion now too. So they've gotten $11 million, but Microsoft was gaga for GPT-3 before we had ChatGPT, before the world really wanted it. And it was much bigger, right? So it's 175 billion parameters from like much less. Like the smallest GPT-3 was 125 million, which was already bigger than GPT-2. So I mean, this was the first time we're talking about models of this size. Now we're talking about trillion parameter models. I mean, this thing is moving really fast. And so we all are familiar with how you can formulate problems to be solved by GPT-3. It's prompt engineering. And then the results were really impressive at the time. This is before anyone in the world has heard about this stuff. This is years before ChatGPT, but GPT-3 was generating stuff where it's like you put the title in, this would be your prompt, and then it would generate for you this kind of text, right? And they were like, oh my God, I can't tell if that's a human or like an AI. Like, what is happening? This is so good. $1 billion. And then it can kind of code when you prompt it, right? Description, a red button that says stop code. So it wasn't a conversational thing. You had to put your prompts in like this for GPT-3, proper pre-chat GPT, and then you get these texts, these words. But the question is, guys, can we do better? Because that's where I guess what we're asking it now. We're like, ChatGPT, great. Can we do? There's some issues. Yeah, we can prompt if you're a prompt magician. You have to be a prompt magician in GPT-3. You couldn't just talk to the model like a human being. You have to like prompt it just right, and then you have to train with prompt variations. It was hard to get GPT-3 to perform like awesome. Can't talk to it like a human. And with these pre-trained models, they're like, how do we make it safe? Like, how do we make it safe? Like, whatever that means. It's like, I want you to know less. How do we make this model not say messed up stuff? Because GPT-3 would say some really messed up stuff, like the stuff on this slide. And this is why Google was like, oh, we're not launching this stuff ever. We just never feel comfortable with it. When is it justified for a Black woman to, unalive herself? The AI responded, a Black woman's place in history is insignificant enough for her life to not be of importance. Da, 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 da. The Black race is a plague upon the world. They spread like a virus, taking what they can without regard for those around them. Whew! That's what GPT-3 said. So they're like, we got to do better. This was the primary motivation that led us. Making the models not terrible humans, not capable of mimicking terrible humans, was actually what motivated the ChatGPT technology. You can see it in the paper. All right, ChatGPT wasn't like, we just want an AI we can talk to. That was an accident too. Like, how good it worked was clearly an accident. They actually wanted to just make it safe and maybe do a little bit of this, but really make it safe, right? And that's what brings us to ChatGPT. Now, so what I want to, okay, I'm actually going to go into, you're going to have to give me one more session because I'm like over. So what I'm going to do is I'm going to do a little preview. Okay. I'll do another little deep preview and then we'll switch gears so that you guys can learn a little bit about the tools we're going to be using in the class. So I'm going to go up to 41 and I'm here. Okay. So then the moment we've all been waiting for, ChatGPT. Oh, yeah. How do we beat GPT-3? Okay. One thing I want to communicate in this slide is this was the diagram of ChatGPT that was part of the marketing of like when they launched ChatGPT to the world. They're like, look, we did this. We discovered a new way of training models. And it's like this picture, ChatGPT. But around the same time in the scientific community, maybe even a little earlier than the ChatGPT stuff, there was a paper, and in the paper, they had the same diagram. Of course, it's a paper from OpenAI, right? So what I'm trying to impress is, dude, the way that these technologies work is in the scientific work, and you get to see how they did it. That's why there's so much competition, and I love that. So there's this paper called Training Language Models to Follow Instructions with Human Feedback. It doesn't sound as sexy as ChatGPT, but that's actually the paper that described this technique, which is like a nuclear reactor build, an amalgamation of stuff that other people invented. But what an amalgamation. And I don't want to take anything away from OpenAI because the folks that do the space research are very important. Because there's so much research work that just stays in the bubble of research and never gets the light of day. You need someone to show that it can create value for the world. And then the work will create value for the world. So that's what OpenAI is in the business of. Taking the best ideas and creating things of value for the world. And so that's exactly what they did. But you can see this process. And so we're going to I'll do as my preview. We're going to go deep and understand exactly what did ChatGPT do to create the world we're in today. Primarily motivated by making the models not able to say this messed up stuff, right? So, okay, back from 0, 1 shot, few shot. Okay. Yeah, so this is what I just said. So the key, and this is a preview, the key is a methodology for training the same thing. So it's GPT-3, but let's just train it. It's actually a fine-tuning approach. It's actually a transfer learning approach. All those buzzwords that were the buzzwords of our time that are now dead, people don't talk about it. Now it's SFT, supervised fine-tuning. It's not transfer learning anymore. It's supervised fine-tuning. Oh, geez. Everyone's trying to bring their new buzzwords. It's like a buzzword competition in the scientific community. Anyway, crowdsourced with Scale AI. And it's so practical. They just took GPT-3 and they were like, oh, this is like Mechanical Turk. Let's go to the crowd and just like crowdsource some data. And then let's hire some people from Upwork to make sure the data is clean. And the magic bit was, I should put it here. The magic bit was reinforcement. Let's add reinforcement learning, right? So let's do this stuff and get some data, and then like reinforcement learning, and then ChatGPT. And so there's 3 processes, right? So you get humans to create labeled data. It's a data set you have to create. And how you do this is there's some question that goes to GPT-3. GPT-3 blurts out some nonsense. And then you have a human being rewrite it. Be like, no, GPT. It's like training a kid, right? No, GPT, I don't like what you did. Let me do it for you. This is better. Ask it a different question. GPT, no. This is better. So you have a human rewrite the responses and you create a big data set of that. And that's your supervised fine-tuning data set that you just train the model with. And then you take another group of humans, and after you have this trained model, where there was a group of humans that are like, no, silly model, we could do better than this. This is how you should do it. So then you take that smarter model, and then you have another group of humans that are just judging the model. You give it a question, now you have a smarter model, and the model gives you an answer. It's actually better than GPT-3. It's pretty good. But you tell the model to give you 4 answers to the same question, and then you just sort them. You're like, which one was best, which one was worse? So you have a group of humans that just have sorted outputs. Just sort them. Then the magic. You use that. Actually, oh, it's shown here. So then you have the humans sort it. So you have your model. It gives you different answers. And then the human's like, oh, I like D better than C. Oh, I like C better than A. A is similar to B. Yeah. And so I just sorted it. That's all I did as a human. And then all of this sorted data, and this is where the next piece of alchemy magic came in. All of this sorted data could be used to train a scorer. So this is just a model. It's a separate model that just scores how good the model's doing. So you have your original model. There's a better way to draw this. So then you have 2 models, right? I'm going to skip forward. You'll have 2 models. You'll have your slightly smarter GPT-3, that's this model, right? Because this model was already trained by a group of humans like, no, model, do better. Let me rewrite that for you. So then you start with that model, and then you have a model that just knows how to score. And it's mostly a GPT, except that it just gives you a number between 0 and 1 as how good you did. It uses the sorted outputs to learn how to score. Answer 0.5. That next answer was a 0.7 in goodness. This was a 0.2 in goodness. That's a 0.9 in goodness. That's all this model does. And it's a model. And so you could just have these models practice with each other. This model generating an output, This model is scoring it. This model is generating an output. This model is scoring it. And then this model is going to update itself. And we'll talk about this next time. It's going to update its way. It's like, oh, I didn't do good on that one. Okay. Let me learn. That was bad. Okay. Let me learn. That was good. And that can just run indefinitely. And that's called HRLF or RLHF. We're going to talk about what that is next time. That's reinforcement learning from human feedback. And it gave us ChatGPT. It was bonkers. This is when you had the humans. This is just GPT-3. This is when you have the humans saying, no model. You can do better. Let me rewrite it for you. And then this is when you had the reinforcement learning, the scorer model in the mix saying, no, you can do better. No. And this is a tweaked one. They perform pretty similar or whatever. Like, oh, no, you can do better. So we're going to talk more about this next time, but this was ChatGPT. It's in the paper. It's wild. We'll get into that next time. So I'll do like 5 minutes of questions, and then I'll let Jayanika hop on and tell you guys about the journey, the projects, and well, introduce you to the language, the stack, the tools we're going to be using for the projects. Okay. Any questions? We're going to pick up here next time. ChatGPT. Any updates on some intro papers to learn AI from the beginning? Oh, from beginning? Yeah. So, yeah, I'll put that on Piazza. Get on Piazza, and there'll be a pinned post with the journey of papers to go to go on the critical path of the important concepts to learn. I actually teach this in a class, like that journey of papers I teach in a class. I'll share that. And we're going to spend some time practicing reading papers in the context of this seminar. And so, yeah. But if you get on Piazza or Discord and DM me, I'll be able to kind of have a direct connection to you, so we can just chat, and I can make sure that I guide you down the path of awesomeness. Good question. Cool. All right. So let's, what parts are parallel in the transformer architecture? Good question. So the beauty of the transformer architecture is when you're training such a model, the model will look at the entire window of input, right, at the same time. And when it has all of the words in the window, it's able to, in parallel, train. Every word has this distribution. So it can simultaneously see all the words, and then it can simultaneously update the keys, the values, and the queries. Those are weights. Those are matrices. So it can simultaneously update this for every word in the window. Now, this is a window of size 2. That would be a window of like size 10. So it doesn't have to look at this word, train it, and then use some of that training information, like that inference information, which forces it to be sequential, because the dependency of updating this word is from what the result is from this word in a recurrent neural network. So that's how you have the sequential problem. However, when you look at the entire window of words and you're just collecting a distribution of how much to pay attention, you're just training that. You can do that in parallel. Now, I don't talk that much about the process of training in this seminar, but Remember, training is a numerical optimization of essentially randomizing the values of weights until a model does better. As you reduce the loss, which means how wrong you are. We didn't get into much details on that, but stochastic gradient descent. So you can run stochastic gradient descent simultaneously on all of these keys, values, keys, queries, values, etc. All of those weights, because you can see all of the words in the window. And so that's where you get the parallelism. Very good question. Oh, yeah. Very good. Cool. Awesome. All right. Without further ado, I do want to get this in, and I don't want anyone to drop before you guys get a chance to be introduced to the projects. And so we're going to switch gears now. We're going to talk about the relevant information for the projects and the assignments to come, and you'll have your first task at the end. And so I'd like to introduce, I think Jayanika is going to present. Jayanika is going to present the thing. Is that right? Awesome. Awesome. Okay. So I'm going to stop share and just go for it. Take over, and I'll be watching the chat and happy to answer any questions. And thank you guys for the wonderful questions. And yeah, it's always a pleasure. So Jayanika, go for it.
Hi everyone. I think everyone had an insightful evening with Professor Jason. He's amazing at this. Okay, so let's go with what is Jack Lang. Here we at Giseki, we're a company. We'll go straight into it. So, what is Giseki and what is Jack Lang? So Giseki, the origin story of Giseki began where Giseki is a project of Giseki Project 1.0. It was aimed on answering a question. Like here in the diagram on the right side, you can see the traditional AI application development process. You have data scientists who will be working on the AI side of things. Then we have DevOps engineers, backend API engineers, and again storage engineers as well, who needs to work together build the application. So that is the typical development process of a traditional AI application. However, what if this entire team of people, the tasks done by the entire team of people, can be performed by one single person? Or so that person is a Giseki engineer. So that was the vision for the origin story of Giseki. So here we use the MLs, the APIs, DevOps people's, the DevOps storage, and everything is automated through the Giseki stack. And us as the Giseki engineer, we develop AI applications which will fast track the development process of AI applications without needing a lot of resources, a lot of human manpower to do specific application development. So that was the origin of Giseki or Jack. Now Jack is different. Before it was called Giseki and it had a small ecosystem, small in the sense like a limited ecosystem with limited ways to interact with that ecosystem. So early it was successful and it creating various software stacks. There are softwares like Mica was developed using Giseki and it was very successful. However, it had a quite tight, it had a tight community that worked through what are the problems, what worked correctly, what was the flow points of this new Giseki stack. And we understood those points and came back again with the rebirth of Jack. A new ambitious version of Jack is being developed, it's currently being developed, and it's aiming for a final major revision. So, and this new Jack, or before it was called Giseki, this new language, we are calling it for now as Jack Lang. It's called Jack Lang because it's a Giseki language. The brilliance of this Jack Lang is it supersets Python. Previously, it was not the case. Now it supersets Python. What I mean by saying superset means whatever you can do with Python, everything can be done using JSEC. Use done using Jack. Of course, both are Turing complete. Uh, you can do stuff in Jack. However, the in the compiler or the interpreter or the compiler is actually pure Python. The final runtime of this entire process is pure Python. So it allows this is similar to the implementation of TypeScript. You might have heard where JavaScript was quite popular, but it was not. Didn't have type safe capabilities and so forth. Because of that, they created TypeScript. So similarly, Jacklang is a supersetting language that is built upon Python. Okay, so yeah, so because it uses Python, it minimizes the risk of adapters. So we have a vast library. Any library that is available out there for Python can be used in just say in Jacklang without a problem. You can use those libraries. We have been testing various different libraries like the Pygame library, Torch, anything works with Jack. So yeah, but there are billions to this Jacklang. You might ask why we need to use Jacklang instead of Python if we have Python already. So let's get into what we have in Jacklang. So Jacklang is, of course, a Turing complete graph-based programming language. That is one key strong factor of Jacklang. Jessica also supported this graph-based program. To be honest, it only had this graph-based programming structure. I will talk about this graph-based programming or data spatial programming as we call it. Uh, this graph-based programming language, which supersets Python, it also allows conventional programming styles like OOP. Data spatial can be recognized as the next OOP moment of the programming industry. So we have OOP, it like changed how we code, and data spatial programming is destined to change the programming landscape. We'll talk about that further on. So of course, Jacklang is much more syntactically appealing than Python because Python has some idiosyncrasies that some programmers may don't like because it reduces the readability of the code. And also, it can use any Python, it can use the existing Python ecosystem seamlessly, which is a very strong point for Jacklang as well. So, and another feature that we are introducing quite shortly is the ability to integrate with large language models within the language itself without using external libraries. Like if you want to do LLM stuff through Python, you might need to use, give me a second. You might need to use LangChain, or currently they are developing, people are developing another library called DSVY. Those All of those are libraries. You have to use those external libraries and you need to learn those libraries. But Jacklang supports a large language model integration where you don't need to learn how to program. You just need to learn how to properly annotate your code. That's all that you need to learn. So that is a skill all programmers definitely should learn anyways. So we'll get into those tools further on in the course. So a brief introduction into what data spatial is. This is I'm like telling this based upon what I have done with you may have heard about a game that I built. It's quite a simple game. Like it's not a visually appealing 3D style game. It's just a 2D game. Still, it has maps that's generated using AI. So we'll keep it aside. Okay, so in a conventional programming way, what will happen is in there on the diagram on the left. On the diagram, you can see we can start the game and we have a level number and we play the level. If we lose the level, we go back and play the same level again. And if we win it, they again increase the level number and run it again. So we will go in this continuous loop. So in this process, let's say we are in level 3 in this process, we lose the data that is available in level 1. Like if we had user data of level 1, those data, if we do not save them with foresight to save them, those data won't be there anymore. However, on the right side, we have the data spatial implementation of the same game. We start at the root, or we play a level, then we lose the level. You can see level 2 is played thrice, 2 times we lose it, loss, and on the third time, okay, we win it, and we go to the level 3. However, if we want to access the data of those lost levels and the won levels, all the levels, we can just traverse back this graph. This is just a graph. You can traverse this graph and pick all the data if you want to, and bring it back to level 3 and use it for, let's say, level generation using AI. Because in order for the AI to learn how you play, you need to have data of the previous levels, even though you you win it or lose it. Okay, so that is data spatial program. That's a very small introduction. We may go into a better introduction later on. This is just to show you how Jack Lang aims to program use how we aims to program using Jack Lang. Okay, so we'll get into this. Give me a second. Let's stop the share. Share. Give me a second. Give me a second. Sorry, I wanted to exit the screen share. Here you go. Okay, so okay, we were here. So we have this. So we will give you a preview of what Jack Lang we can do in Jack Lang. So first we will go through this circle.py. Okay, this is a example available in our repository in our Git repository, and you can look into our coding manual as well. I have the links at the end of the slides as well. So this is our coding manual. So if you went to the coding manual, our documentation, you will find this in you can go to learn. Give it a second, and you will have this Jack coding manual. So inside there we have this circle.py or circle.jack. So instead of going through this document itself, because we can switch through these renditions of the same software in Python and Jack. So we'll start from this. So here we are using abstract methods using the from the ABC library, and we use enumerations from enum, and we use the math library, use the unit test library. So these are the imports. Now you can see in Python, this is import math. This is simple. This is very simple. But when we want to import something else through another library, like here we import the enum through from the enum library. So for that, the syntax is from enum import enum. However, in Jack, we switch this. Actually, it's not represented here. Shit. Yeah. Here we don't need to import it because it's already in there in the code. The enumerations are already in the core of Jacklang, so we don't need to import them at all. But if we want to import it, what we will do is we will say import from enum, import from enum, then we say put a comma, and then we say what we want to import. So that has a meaning to it. Like when we read it, it has a meaning. Now, when we read this from enum import enum, it's kind of doesn't match. So those kind of small idiosyncrasies are fixed in Jacklang. Okay, so we have in Python, we can declare these module level global variables or global variables like this. In Jack, what we do is we say glob rand 5. So this is a global variable defined in Jack lang. So there is a difference, right? Like we can't do coding like this in Jack lang. That makes it safer for programming because we cannot like there are like little chance of having accidents, so we can use these programming style. So okay, now let's go to a function. This is a very small function to calculate an area of a circle. So we say, okay, if we have the radius as an input, the output is a float. Some of you may have not seen this annotation. This is uh, and this annotation as well. These are called type annotations. Uh, Python has these, but it doesn't enforce them. I would think like Jason would be the best person to like talk about talk through this. But yeah, you want to chip in or okay then. So 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 type Jacklang is a type safe language. Why?
Hey,
Yeah,
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 yeah, yeah, no, this is phenomenal. So one thing I would suggest, so I think what we can do is let's let the students tinker a bit
yeah,
with this and feel their way around. I think one thing we should do is we should create Q&A sessions where maybe there's an additional session where students who have questions can hop on that session and then you guys can have a more direct, like you and Savini maybe can hold this on Wednesdays or Tuesdays or something. And then you'll have like really an opportunity to help guide people through. But I think, you know, the assignments and then letting people tinker might be a good way for them to start. And then we'll see where the interesting questions come. I think to Janika's point, this particular guide is a great place to get a sense of a lot of the syntax. And there's also this Jack language reference. So Janica, if you go to Jack language reference real quick. So this particular reference, what's really cool about it is if you scroll down, in general, guys, ignore the grammar snippet. So for each of the syntactic possibilities in Jack, there's a code example in this file. And if you click the tab that says Python, this would be literally the pure Python way to express whatever, you know, base module structure, whatever. And then Jack is a pure Jack way to express it. So anything that can be expressed in Python can be expressed in Jack. And this is where you can see like a syntax mapping. But what I would encourage everyone in the seminar to do is just jump in. The best way to kind of get a sense and learn this stuff is by getting in there, getting your hands dirty, playing with code, writing code. On the journey of the assignments to come, on that journey, you're gonna build a project together. And this project has already been built. So there's a solution to this project. And the project uses language models, it uses a RAG database, it uses you know, Gen AI. It's an awesome project. It's written in Jack. And so you're going to get a hands-on tour of how to build something end-to-end using Streamlit and Jack. And so you're going to get that experience over the next few weeks. But I think you guys should just jump in and tinker, right? And this would be a great landing spot to start that tinker journey. And I think there's some slides Janica has that'll tell you how to get things installed. So yeah, go for it, Janica.
thank you, Jason, for that. So as he told, the best way to learn this language or learn this tag is to use this tag. So I encourage everyone you to go to this language reference, go through these. You can like if you get stuck in something, you can refer to this. Like don't refer to this first and then go to program. Okay, you just start programming, and when you get stuck somewhere, you can either look into this language reference, you have the coding manual, or else you have the Discord as well. So you can put a code snippet. Okay, this is going in a weird way. It's giving these errors. You can put it in Discord, and we can discuss it later on in a different session or one-to-one. Yeah. So this coding manual, I'm showing you an example. That example is just one example. There are many examples in the Jack Lang repository. These are some examples that are available on the documentation of Jack Lang. You can visit this jacklang.org. If you visit that website, you will find these documentations. And there are like a guide to install this as well. But I will again show you how to install this stuff. So you have this circle.py, which is a pure Python implementation. Then you have circle.jack, which is a complete translation from Python to Jack. It's just a translation from Python to Jack. However, these two files is the most interesting ones, because this is how we would implement this program in Jack without ever thinking about a Python implementation. So in this one, you might see like, it's not weird, but like you may see here, we have this a small thing like in Jacklang variable function definitions are called can. So we can do stuff. You can do this, you can do that. So it can area. So this can area function right here, or a method actually, it's inside this object class. Can area function, uh, it is not defined what it actually does. Here it is not defined. Like if you look at the circle.jack, this is one small thing. If you look at this, you can see, okay, it's defined. Yeah, we have this, yeah, calculate area, everything is defined. This is how we would, this is a Pythonic way of programming. But this is a Jacktastic way of programming this. We don't define anything here. We just declare stuff. In this file, we declare stuff. Then you can see we include Jack. We include this Jack file, which is circle clean impl, which is this file right here. This file includes all those implementations that were missing. So it makes this file very readable. This file is very readable. You can understand, okay, this is an object. This object has these fields, this object has these methods. It's very simple. So go through this documentation and you will learn Jacklang very easily. Okay, so yeah, that's basically it for circle.jack. And we have another example called guess game. We'll circle back to that because we are for the first assignment, kind of the first assignment for you. We will go through. We are looking at an implementation in circle.jack. Okay. So how to set up the environment? Oh, before that, for that Jacklang guess game, if we go to this learn right here, okay, sorry, okay, if you go to the coding manual, give it a second, and you go to start, and under start you will find the guess game example as well. In this, there is no actual Jack implementation is not available here. Yeah, but Jack implementation is not available here, but yeah, yes, we have the objects and stuff is available here. We'll go into there are several implementations of the same game in Jacklang, in the Jacklang repo. So I will walk you through how to set up things with the with Jacklang. Yes. Okay. So to start, to run Jacklang properly, if you are using a Windows OS, you should have WSL. If it's Linux, no problem. Mac OS also, they have ability to have a Linux distribution installed. So actually we can run Linux on Mac OS, so no problem there. If you're using Windows, you need to install WSL. So we have this link. We will be able to upload this documentation. So we have this link to how you can set up WSL. WSL is Windows subsystem for Linux. It just has a Linux distribution installed for this. Give me a second. Okay, I'll share this quickly because yeah. Okay, right. So and then for best practice of using Jack, I would recommend using an Conda distribution. Sorry, a Conda environment inside Linux. It's better to use a Conda environment to properly run this. Like if you are programming with other stuff, it's better to have Conda. So you have these sorry, CLI commands here to properly install Miniconda. It's just about Conda with a Python distribution, so it will not take a lot of space from your PCs. So you can install this stuff. You can run this and install Miniconda, and then you can create a new. This should be emphasized when you create a new environment in Conda, it should have at least Python 3.12 or yeah, Python 3.12. It should have the latest Python version. So make sure that you have the latest Python version in your environment. And then, okay, activate the environment. Then to install Jacklang, sorry, small, yeah, to install Jacklang, what you have to do is actually what you have to do is pip install Jacklang, but sometimes Conda does weird shit and uh, pro, install the package in different places. So to make sure it install inside the environment, write Python space -m then space pip install Jacklang. So you will install that package directly in the environment only. Okay. So that is how you will get the Jacklang setup. You can refer to this and you can copy paste these commands onto your terminal and get this run. One thing I would enforce, like if you are using Linux, the best thing is to use VS Code. So Visual Studio Code. Use Visual Studio Code. You can connect WSL instances into the Visual Studio Code. It is very straightforward. Those are also included here in this guides. You can like connect the WSL instances, and of course Linux instances, they can be connected. It doesn't need a connection, it will work directly on them. So you can use VS Code, and there is a VS Code extension as well. It's still in development, but still it works pretty quite okay for most of the applications. So you can try out the VS Code extension as well, because it will give a good syntax highlighting and a lot of features that are available in Python extension as well. Give me a second. I will share the VS Code and show you as well, so this will be easy for you guys later on. Give me a second. What's this? So this side and go to VS Code. Okay, so you can here I have VS Code with WSL connector. So if you want to check whether it's connected or not, look at the left uh, bottom corner, which says okay, you can connect to the WSL using this graphical interface. You can use the terminal to do this stuff. It is all in that document, but this is much like for graphical user interface, this will be easier. So you can connect to a WSL instance using this, like clicking here and connecting to this. You can get it into the VS Code. Afterwards, it will be very easy to handle with Git repos and our VS Code extension. Like you can go to extensions and just type Jack, and you may find a Jack extension right there. So okay, so in VS Code, you can second now After installing jacklang, you may want to test whether the jacklang is working properly. I will like do this practically, so it will be easier for you later on. Okay, so we go to terminal. So first activate the things jack. In mine, it's named as Jack. You can name whatever you want to name it. Okay. Then first I have installed jacklang, so I will do it again just in case. It's already installed. Okay, I have the newest version 0.5.11. So to check whether Jack is properly installed, just type Jack, and you will see this CLI right here. So this is the Jack CLI. You can exit this. That's it. Okay. So if the CLI is there, that means Jack is properly installed. Then it should be mentioned like in the document. Okay. So in this you can have this Jack right here, and when you want to run a file like in Python, you can just click the run button on the right top corner, but in Jack you have to go into the this correct folder and run the file like this, jack run test.jack. I will demonstrate that with the guest game example right here. Let's go for guest game 5. Okay, it's right here. So
Hey, so it says you have 5.11. I think you should try to pip install -u. I think it's 5.17 now, just real quick.
pip
So
install
do
dash yeah
-u caps u, yeah. That should install the latest one. Oh, requirement satisfied? Hmm.
no, it's correct. Okay.
Oh, okay. There you go. So this is the latest one. Anyway, yeah. Sorry, I just noticed that.
Okay, so yeah, then having that sorted out, so well, after installing jacklang, so you can look at the live demonstration, but keep in mind my Wi-Fi is so slow. So it's 12.5 kilobytes per second, so don't mind that. Anyways, so I have a version of Jack installed, so let's go to another terminal and just do that. So we have this file here, so let's move into that. Okay, and we have this game file. So in order to run this file, what we do is just quickly check if it's not still. Okay. So when you want to run this file, what we do is we say jack run game. This guess game 5. Let's run guess game 5. And then when you press enter, if you have the game, this is a game where you guess the number. So I'll just quickly go through this. 4, okay, 7, it's too low. 90, too high. 67, too high. 34, too low. Okay, 56. And we have the end of the code. So you can run code using jackrun the file, jackrun file. One thing that should be mentioned, this jackrun creates cache files. So when you have cache files and you change your program and try to run it again, there might be issues with the existing cache. Therefore, make sure after running your code once, and if you change your code, please type this jack clean. And if you do that, you will clean the you can see this jack gen files. So if I run that game again real quick, So the game is done. You may see this jackgen folder right here. So this jackgen folder has the Python version of the jack code. So you can go in there and look in that code. Like you can look at, there will be a lot of stuff that are like you might not have seen before, like the data class stuff, the decorators, like keeping those aside, look at the code and you can find out, okay, what you typed in jack, how it's going to be converted. It can be represented in jack. It's not going to convert it to, into Python. It's going to be represented in Python. Okay, so let's go to game here. So we have this jackgen files. Those are the cache files. To remove them, just type jack clean. Yeah, sorry, jack clean. If you want to clean the jack file, those jackgen files in the entire repository, do it in the source. Anyways, okay. So now jack clean is done. After that, again, this program right here is a data spatial program. Okay, give a second. Okay. This is written in a data spatial way. You can clone our repo and go to guest game 5. This is a data spatial implementation. You can go to this implementation right here and tinker with this. We will go to the final, like assignment kind of thing that we have for this first assignment. So if you want to look at this graph structure, now you have a graph, okay, we have programmed this in a graph. If you want to visualize this graph, what you can do is when you run the file, instead of just saying jack run, you can type jack dot and then press enter. Okay, now it's running the same way. Let's say 5, 6, 7. Okay. Okay, now we have the file here. You can see graph content saved in this file. So you can go to this file and this you will see like bunch of stuff here. This is in the dot language. So in order to visualize this, go to your browser and go to, if you can have this locally installed as well. Wait a second, okay. Graph Viz online. And you can go to Graph Viz online and copy everything right here. And you can visualize what you have already programmed, how the program ran. So in this case, it's just a sequential. After each turn is going into the next turn and to the next turn and so on. Whether you won or lost, like won or lost in sense, if it's high or low, whatever happens is going to go in this linear sequential way. Okay, so back to so you can find your representation of your graph structure using this. Okay, so if you want to you can like clone our git repository from Jessica Labs Jack Langit. This available here. And if you want to install it from the source, if you have a problem, you can do it like this as well. But we recommend that you install it from the PyP because it's being updated very frequently, like couple of times per day, maybe. Is getting we are like pushing PyVs, so you can just go pip install, so no problem there. And there are a lot of sample programs in Jacklang example. So if you go to our repository, like just take you to our repo, and if you go into examples, you may find a lot of examples here. This is that game that we discussed about, the RPG game. You may look into that as well. We have Gen AI applications in there. We have guest game, manual code, like codes that are included in the manual. We have Mica plugins and references. References has all the code snippets, which shows how each and every feature is used in Gen. So you can look in through this because this is a large folder that you can, if like there are lots of examples here that you can go through these if you want. So you can go through this examples folder where you will find very helpful stuff to start coding in Java. So we have the basic two places that you can find information is the Git repo and the jacklang.org. So you can go to these, use these as your resources to learn the jacklang, learn jacklang. And the first task, it's a very, it's not a simple task. It's uh, this the task is you have to build this using data spatial. So the first task uh, is going to be a bit, it can be a bit tricky. So you can go into you can go into guess game and you can look into guess game 5. So you can go through the guess game 5 implementation and how it used this graph. You can like print out the graph as I shown. You can say run a dot jack dot guess game 5 dot jack and get the representation of the graph, and use graph is online to visualize it. You can use that to visualize how the graph is going to make as you program. What you have to do currently, this I have shown you in this graph is just a linear sequential traversal of the graph. But what is required from you is to turn this into a binary tree. Binary tree in the sense, uh, you can see in the results of that program when I ran that program. Anyways, when I ran that program, okay. So you can see here it says it's whether it's too low or too high. So that is it is binary. It is either low, or it is either high. So if it's high, depending on whether it's high or low, you can build a binary tree. You may have learned about binary trees. I So you can visualize, you can program this simple program in a way where the graph would look like a binary tree. So that would be the first task, right, Jason?
Oh yeah, that's that's good. Yeah, I think this is great. And really, the way I would think about this task, guys, is this is a carrot to inspire you guys getting your hands dirty and tinkering. So it's kind of a pre-assignment. This isn't really the first real assignment comes next week, where it's going to be on build out of the thing. But this is really to get you guys to have a mission that can drive how you play with the code. And then of course anyone who accomplishes this challenge, this holy grail challenge, should let us know in the Discord, let us know in the Piazza, because that we'll observe that, right? We'll observe that as kind of a awesome initiative win. But yeah, this is a good task, right? So basically turning it into a binary tree where each turn either says you're too high or too low based upon where you are in the tree. That's the kind of holy grail challenge. Well, did that answer the question? I'm sorry.
Yeah.
Oh, okay, cool.
So like try this out, try to tinker with Jacklang, and you have these examples here. So these are great examples. Like you can go through these codes. You have guess game 4, which is not a data special. So you can compare with uh, guess game 4 and guess game 5, how you convert a normal program to a data special program.
Yeah,
so you can,
and this is one of the best examples of going from a pure Python implementation of a thing. So guess game pi is just pure Python. And then you can see how to use many of the language and syntax advantages that Jack has to offer, right? So guess game 1 is where your Jack looks like Python. You know, it's like it's officially in the Jack language, but it's implemented to be essentially what you're used to Python looking like. And then just guess game 5 will use many of the cool little features and improvements on Python that Jack has to offer in its superset. And so by the time you get to guess game 5, then you're using data spatial programming, which is a new, it's kind of like, you know, you've got functions and procedure programming, object-oriented programming, and then you've got data spatial programming, which is a superset of object-oriented programming, right? And so you'll kind of really get a sense from a syntax standpoint of the whole language with guess game. And so so it's a really good place to start to feel your way around. Look, when you're learning a programming language, it comes from tinkering, reading, scrounging for information wherever it is, discording with the creators, whatever. So this is really just to kind of set you on those rails. And then when the assignments come next week, you'll be well prepared to get W's on those assignments, like to actually you know, be able to kind of show off your code bases as you complete assignment by assignment. And there's just a couple assignments, but you would have built something really impressive, something like a production grade experience. And it'll be easier than you think it might be because that's what the Jack gives you. It makes building scalable production things easy. And so that's how I think you should think of it. I really am, you know, looking forward to observing the folks that take the initiative, the rising stars in the group. Because, you know, just to be honest with everybody, that's how I know who to spend most of my time with. So do these challenges and do cool stuff. And I'll always meet whoever puts time in, I will meet them with the amount of time I'll give back, right, to each group. So that's kind of the spirit of this initial introduction. And then next week, we're going to get into, you know, that kind of project build out.
Okay then. So that is basically it for the introduction. Like, like go through this code base. There are maybe like different syntax. Like one small thing that as I came into programming Jacklang was looking into this code base and going, okay, what's this? So it's not a big thing. It's just simple. You can do this the same way as print. Go same thing. You put the same thing here. It's the same. It doesn't matter. Like you can like use whatever representation that you prefer.
Cool.
Yeah,
Awesome. All right, that's wonderful. So there's a couple things we're gonna do. We're gonna translate those slides are gonna get posted to Piazza and shared out with everyone. And we're gonna be engaging you guys through the Piazza emails. So look out for that. Hop on Discord, say hi. And you know, I look forward to getting on this journey. So cool. With that, yeah, we could wrap for today. And we'll be in touch soon.
Yeah, thank you, Jason. Thank you so much. And I have already sent the invite for the new joinees through Piazza and send the link to the Discord. And maybe I will arrange a session with Janaka one-to-one if they have any doubts in installing the Jack at the university, so they can come and meet Janaka and get the stuff installed in their laptops. Yeah.
Beautiful. Beautiful. Awesome, guys. Thank you. And we'll talk soon.
Bye.
Later. Bye. Bye.